Hi everyone. It's my pleasure to be your host today, and we're here for a webinar that's called From Research to Real Time towards interactive example-based video stylization. And this is going to be about amazing technologies that was presented at last year Technical Papers program. And I forgot to say that I'm this year Technical Papers program chair, Sylvain Paris. And if we can go to the next slide. So our speakers today are Andre Texler, who is a research scientist at Samsung Research America. And before joining Samsung, Andre prepared his PhD at the CTU Prague in Czech Republic, where he worked with Daniel Sikora. And if we can move to our next slide, because Daniel is our second speaker today. So Daniel is a professor at the Czech Technical University in Prague, where he works on computer graphics and stylization. A fun fact that I just learned today that Daniel actually does not know to draw himself. Doing research in computer science in this domain is his way to express himself and to create this amazing works that we're going to see. I'll keep it short and let Andre and Daniel present. Just to give a bit of context, just to give a bit of context, I had the chance to work on that type of technique by myself, and it's extremely hard. And what we're going to see is still among the very best results in this domain. And I want you to really appreciate that what we're going to see is really the state of the art. Just before we get started, don't forget to ask questions. You can use a Q&A pod in Zoom, and we'll go over the question at the end of the webinar. So Daniel, take it away.
Perfect. Thank you, Sylvain, for a nice introduction. So let me just start with some, let's say, relatively kind of short intro of why we are doing this, and then we will go more deeply into details with respect to the paper that we presented last year. So let's start with the overall motivation. So why we are doing style transfer, why we are doing stylization. So basically, you probably know that what you probably can see in the cinema today, and if it's animated movie, you will get something which looks like super cool physically based rendering, which looks awesome and everybody likes it. But when you ask the real artist, like what would be his dream, like what would be the actual future, like how we envision the actual animated movie look like, he would like to keep his kind of original, unique style in the final appearance of the movie. And that's visible on this slide. So you can see that this is on the left side. It's something which you can get with physically based rendering, but the artist has kind of slightly different idea of how the actual output should look like at the end. And that's basically the actual motivation why we are here and why we are trying to do style transfer, or something which will enable create, let's say, imaginary, which is kind of still depicting the original kind of unique style, but it's changing the actual content. And you probably know, and that's really a hot topic for over the last couple of years, that there is a technique which is called neural style transfer, which is exactly, let's say, cool thing that maybe can be useful for our case. And it actually uses the idea that you can have style image, and this style image is actually something which can be completely different. In this case, we have just a sphere, which is kind of hand drawn on the paper. And then you have also some target content, which is 3D model. And then the idea is to transfer some aspects of this style on the target. So you would like to kind of merge these two things so that the final output will have the content, but will also contain some details which are important for the actual style. So the idea is super cool, and this neural style transfer use neural networks which are trained on object recognition. So there is a belief that they can kind of recognize some important features, and if you kind of merge them, you will get something which would look reasonable. But if you try that, unfortunately, the output is not super satisfying. And here you can see what you actually get, which obviously have two main flaws. So one flaw is that the transfer is not meaningful. So the column is red, but of course, like you would expect that it should be kind of bluish as the sphere. And there is the other problem that you can see that the original high frequency content, which kind of reminds you, this is something painted on the paper, is not preserved, and it's kind of like washed out and smeared, and it's close in color, but definitely not on the, let's say, intricate, let's say, high details that you would expect in the file. So this is actually a motivation for us. So how to come up with something which would, let's say, break these limitations. And so we decided to really look into it more properly and said, okay, we need some more, let's say, stronger semantics. So we need to tell the algorithm what is what. So for example, if you have this 3D scene, we know that the artist is kind of stylizing the actual highlight in some particular way. And we know, because we have 3D rendering, so we can kind of render the highlight of the target. So we also can provide this correspondence. Okay, this is highlight in the source and this is highlight in the target. Try to transfer the style in a way that the actual appearance would correspond to the highlight, which is different as compared to the previous case where it was kind of more or less like color-based mapping. So this is one important aspect. So having some high-level semantics, which is incorporated into the process. And the other super important fact is that we need to preserve the low-level details which are visible in the original size. So this is like watercolor painting of the original sphere. And you can see that in the target image, those like really small details are very nicely preserved. And they are so nicely preserved that it is almost the exact copy of the original. And that's the only way how you can actually preserve the notion that the image is kind of hand-drawn and hard, let's say, to recognize that this is created synthetically. So this is another important aspect. So kind of like preserve the actual original artistic media as much as possible. And we actually developed a method which was presented at SIGGRAPH 2016, which is able to do this style transfer, which satisfy both of these constraints. So it's semantically meaningful at the first place, and in the second place, nicely preserve all the high frequency details. So in this case, you can just replace, for example, the style. So let the artist to paint some different style and also change the target scene, and you will get this result, which nicely preserves these two important things. But obviously, you can say that this is kind of simple scenario because you know the 3D model, you know the semantics. It's kind of like relatively simple, but let's speak about faces, which maybe are something, let's say, more different. So if you have a photo of a face, you don't have the actual 3D information about how it looks like. You also don't have the actual semantic information, so you need to somehow retrieve it. But the problem is kind of similar. So you have some exemplar which have different identity and have some particular artistic style, and you would like to stylize the target person in a similar way, so the actual identity is preserved, but the style is comparable to the original exemplar. For that, we also developed a technique which kind of infers some semantic information, mostly based on landmark detection. So we use some existing landmark detectors, and they are able, let's say, to give us the rough positioning of important facial features. We have also some additional segmentations, so we can detect the actual face segments and hair segments. Obviously, it's depending on the quality of these detectors that we have, but suppose that they work relatively well. And then we actually use the same algorithm as in the previous case, and do some similar, let's say, approach for the actual preserving the actual details, and produce the result, which is kind of comparable to what we saw so previously, but in this case, it's tailored for faces. So here is an example of how it can look like. So, for example, this kind of particular style is super difficult for the neural techniques, and it works nicely because, as I said, it's mostly the exact copy. So it's just a rearrangement of the original style pixels. to the target image so that you preserve the content, but you will actually copy the pixels in a way that you will recognize them in high detail. It's working even for like wooden statues, for example. So it's not necessary to be like a hand-drawn painting. It can be also this most like photorealistic content, or for example, the real stone statue. So this particular transfer is kind of very much compelling, and it nicely shows the high quality of the method it can produce. So that was the actual state where we end up in 2017, and of course we wanted to go even further, even into something more, in the sense that the original method was relatively slow and not super robust. So as I said, okay, there was some issues. So if some of these detectors kind of fail, then you will get some wrong results. So we decided to use our technique to create a large data set and train a network which will do the transition from the original photo to the target stylized image automatically. So it has two advantages. One is that it's fast. So after that, you can do it in real time. And the second advantage is that the network is kind of styling the actual algorithmic output in a way that the actual wrong solutions or wrong outputs from the original algorithm are kind of like, let's say, fixed, because the network will train some manifold, which is a kind of, let's say, is not prone to these like outliers, which typically happen if the original algorithm fails. So at the inference, you can just feed the input image and you will get the actual output. And here is an example how it looks like. So you can do the style transfer in real time. So you can just change the styles on the fly and see the actual output. You can even change the person during the actual capture. And so this is kind of like what we envisioned would be the, let's say, very nice and cool target application for artists to play with stylization and creating the movies which will preserve their particular unique artistic style. And this kind of like motivated us for something which is more general, more generic, in the sense that you will get a video. So there is no like particular content, it's arbitrary content. So you will get a video and you will just stylize a single frame. Let's start with just a single frame. And then you have these two images, and of course, the other frames of the video. And you would like to transfer this style to the other frame so that the actual sequence would be temporally coherent, so there will be not much flickering. The style will be preserved in a semantically meaningful way, so some parts will correspond. So for example, if you have this part around the face, so it will also be stylized accordingly. And of course, it will be reasonably fast, so it can be used in production. So we also, for this case, we developed this, let's say, way how to guide the actual synthesis to get into state that is transferring the content in a semantically meaningful way. We also use the same algorithm for preserving the original artistic style. And the added component, which is important, is that we added this temporal coherence part, which is kind of measuring the difference of the current frame to the warp version of the previous frame in a way that it's kind of reducing the amount of flicker which is visible in the final sequence. And the other problem which we also try to solve is the actual mixing of a content which is going from two different keyframes. So you can imagine that I have one keyframe, but over time the structure of the scheme is changing too much. So it would be probably reasonable to create a completely new keyframe. But then there is the issue that you need to somehow merge these two frames, which looks relatively different, and produce something which is, let's say, more meaningful and let's say allows you to do the smooth transition between different keyframes. So here's an example how it looks like in action. So this is like a real test from a real studio on an animated movie that is in preparation currently. And you can see that for this case, that the first keyframe resists relatively long, but then the person starts rotating, so you would need, let's say, more keyframes. But the method is kind of trying to preserve the actual content relatively well, and so there is no need to have to create like, let's say, keyframe every other frame, which would be obviously like super tedious. So that's the actual idea behind the work which we presented last year at SIGGRAPH. And now I will let Andre to explain you the details of how we actually extended this approach to be, let's say, more ready for real production and more robust to some drawbacks that Andre will also introduce. So Andre, so floor is yours, and I will just stop my presentation.
Okay. Perfect. So I hope you can all see my slides now.
Perfect.
Should be fine. Yeah. Okay, so thank you, Daniel, for your part of the talk and for properly motivating the style transfer task. So my presentation will start with the same method as Daniel talked about at the very end. So this keyframe-based video stylization. So this is the same thing, just different result. And yeah, this method can really well stylize even like more complex sequences. So this sequence of links can be stylized well using this method. But this method, as Daniel said, is not based on neural networks. It's based on optimization, texture synthesis, guided texture synthesis approach. And it of course has some drawbacks we wanted to push and we wanted to get rid of. So this method obviously preserves high quality details, so the result was really nice, and also the result was really temporally coherent, so there was no flickering between adjacent frames in the sequence. But still there are some drawbacks that are really limiting. So it's computationally very expensive. For longer sequences it might take hours to process. It's also data dependent. So if you want to have it temporally consistent for stylizing one particular frame, we need to know the previous frame, because we need to use that previous frame to stylize the next frame. So it's inherently sequentially, it's really hard to parallelize this approach. And also, as Daniel talked about, there is this blending from multiple keyframes. So let's say we have two keyframes in this case. So how it works, right, is that we stylize the entire sequence from one frame, and we stylize the entire sequence from the other frame. And now we need to merge these sequences. So in our work, 2019, we presented how to merge these two sequences, and it somehow works. It works well actually, but it's more like explicit approach, and we wanted to push it a little bit even more forward. And we wanted everything to be as implicit as possible, and we wanted to have some advantages, like we wanted to run it fast, and we also wanted random access, so we can stylize arbitrary frames from the sequence without the need for any other frames of the sequence, or even stylize all the frames in parallel. So this motivated us to explore this IR even further and develop a new method that I will talk about now. We presented this method at SIGGRAPH 2020, and yeah, so our first thing to try in this key-based stylization task was that we wanted to, Daniel talked about face style GAN, the GAN trained to stylize faces. So we wanted to try. We wanted to start with this approach. So this approach can get high texture quality results, as we saw, but it requires huge data set to train. And in our case, we have just one keyframe, or just 2 or 3 keyframes. We do not have large data set. So what can we do? How can we overcome this obstacle of lacking data? And we cannot actually get more data, because the data are really hard to get. They have to be painted by an artist, or stylized by some other algorithm. So these data are not easy to get. So yeah, what happens if we try to train this face style again on just a single training frame? So we have just this image, one training image that is actually painted by an artist. So if we train the network on just this one image, of course the network will strongly overfit. So the network is able to perfectly reproduce the one given training frame, but on all other frames in the sequence, it flickers. It has a lot of artifact, a lot of noise. Of course, it overfitted to the one training frame. What we can do, we thought that maybe simple data augmentation would be good. So we tried a couple of data augmentation techniques. We tried to add Gaussian noise, we tried to add salt and pepper noise, we tried to do some cropping, rotating, we tried to do all sorts of dropouts and stuff like that. And these are the results we were able to obtain on a frame that is slightly different from the training frame, just like few pixels different from the training frame. And it was not good, like no results we are getting very good. So we are wondering that we probably need to change the training strategy somehow, that we need to do some more substantial changes that just simply augment the data set. So inspired by a technique from ZOE 2018, and there is a lot of technique actually that inspire us. So inspired by these other approaches, we propose spec-based training strategy to simulate a large data set. So how it works, what we did is to simulate this large data set. We crop small 32 by 32 rectangular patches from the training images. So these are two training images, and to get the large data set, we can crop very large amount of these small patches. This is this is how it actually, how the whole pipeline actually works. So during the training time, we have input image, and we want to learn how to go from the image on the left hand side to the image on the right hand side. And so we randomly sample, randomly crop, explicitly crop. So we take the patch and we really crop this patch from this image. So there is nothing around this patch. It's just small 32 by 32 rectangular patch. So the network never sees anything larger than this small 32 by 32 rectangular patch. And then we pass the patches through the network. Network stylizes the patches somehow. And we crop the patches from the same location in the corresponding output image, and then we compute the loss. So this training strategy doesn't need to use any particular losses. We just use L1 loss, adversarial loss, and perceptual VGG loss, but we can use any other losses. Using this, we were able to get, we found that we can get some interesting results. And also what's important is that using this patch-based training strategy, we are actually not losing the opportunity to run the inference on full images, because it's important to run it on full image as we want inference to be as fast as possible. But since the network is fully convolutional, there are no fully connected layers, nothing like that. So we can train it on small patches, and then we can do the inference on arbitrarily large images, as long as the features during the training were of same size and same rotation as the features in our full inference image. It works well. So we can take it's trained on patches, we can take entire image, we can pass it through the network, and we can get entire image in one pass very quickly. Our method works real time. So that was one of our conditions why we decided to move away from this optimization-based approach Daniel talked about to this neural network approximation of that approach, actually. And another important or nice property is that so far I explained pretty much the whole method, and I didn't talk about time consistency or about the need for previous frame to stylize the current frame, because there is none. So this works really well if we stylize if we translate just image to image. So we can take all the images and we can stylize them in one batch, or we can take random images and we can stylize them, and output will be somehow temporally consistent. If we do the tricks I will talk about in a few minutes. All right, so we train it on batches, and on the left-hand side, it's a result of the previous method, and on right-hand side, it's a result of this current method. And as you can see, it's not nice. It's not good, actually. The results are not that good. So how come? And we found that the problem is not the batch-based training strategy itself. The problem is that, of course, with this new strategy, we have some more hyperparameters and things we need to tune. So we wanted to do hyperparameter tuning, and for that, because we wanted to do it like more rigorously. So we wanted to have some ground truth data that we will be able to do grid search or some other methods to tune the hyperparameters efficiently, and like really explore a large number of different hyperparameters. But we do not have any ground truth data, right? That's the point. We have just one stylized image. So actually, in this case, we use the previous methods to generate some ground truth data for us. And note that this hyperparameter tuning and generating ground truth data, it has to be done just once. Like we did it in a paper, it's explained there. No one has to do it ever again. Yeah, we found some by doing this. We actually found some really interesting properties of the network. So of course there is new hyperparameter, which is batch size. So how large batches we will be cropping from the images. So we explored a couple of different batch sizes, and also batch size, because usually you want as many images in one batch as fits to the GPU, because it's the fastest way to train it. But we found that it's not the case in our case. Actually, batch size is quite important. I will talk about it in just a minute. And also there are some other hyperparameters we can tune that are maybe not that interesting as the first two ones. Yeah, so we have ground truth data generated by the previous approach. So we take the input image, we run it through the network. We set the hyperparameters, we take the input image, run it through the network, and then we compute the loss between the generated image and between the ground truth image obtained from the previous method to evaluate how this setting of hyperparameters, if it's good or if it's not that good. And here are some observation on hyperparameters. So just note here that because we optimize not only for inference speed, we optimize for practicality. So we want the network to be able to learn, or to be able to, we want the model to be able to train in just a few minutes, ideally. Because if artist is painting, or we want to allow artists to iterate fast. So we impose this strong constraint of 1 minute. So we did a training for 1 minute on one NVIDIA GPU, V100, strong GPU, but still we limited the training time to 1 minute. And then we tried a couple of different batch sizes. So it means how many batches, how many these small 32 by 32 batches will be in one batch. And we trained the network for one minute. And we found that there is like quite strong local minima here. So if the number of batches is around 40, it works much better than if the number of batches is more, for example 500, which is it might not be intuitive, because usually the more batches, more data in one batch size is better. But in our case, this randomness and training the network on small chunks at a time, doing the backpropagation with just limited amount of data is really beneficial for the network to quickly find the good local optima and to quickly learn the style. So we did this for a couple of other hyperparameters. So we also find that that batch size is important to be at around 36 by 36 pixels or 32 by 32 pixels. Of course, having smaller batches wouldn't make sense, because then the network wouldn't be able to learn like any large features. And also having large batches, we would essentially end up with regular full frame training, right? If we increase the batch to match the size of an image, we will have would have the same training strategy as regular image-to-image translation network. So it means it would overfit. And we also try to tune some other things like number of ResNet blocks and other hyperparameters. These other parameters are not that interesting, or they do not. It doesn't make sense to change these hyperparameters. For example, ResNet block, like any number of ResNet block is kind of okay. All right, so with hyperparameters optimized, we were able to get much better results shown on the right hand side. Yeah, so I said that we were like really aiming for training speed. So let's say we have these two. These two images are our training images now, and this is our validation image. And in this video, I show how it converges in time. So this is after 5 seconds of training, after 8 seconds of training. So you can see that it converges really fast. So how we created this video, we just save the validation output like every few milliseconds, and you can see that after just 16 seconds, we are optimizing the hyperparameters and everything for 1 minute. And if you are doing this after just 16 seconds of training, it learns quite a good style transfer model. But there is one more issue. I will just quickly go through slides as we are kind of running out of time, I guess. So there's one more issue, which is temporal consistency. So our method is not using any explicit temporal coherence. So meaning we do not, there's like no optical flow, nothing like that. We do not need the previous frames to stylize the next frames. And so the final result somehow flickers. So we found that this flickering is happening because actually in the original sequence, we cannot see it by the naked eye, but in the original sequence there is some amount of noise because it was obviously captured in very bad lighting conditions. So there's some noise, and if we remove this noise and we propose to use motion compensated bilateral filter that accounts for motion, if we remove this noise, just by removing the noise from the input video, we can get much better results in terms of flickering, which means that the network somehow amplifies the noise that is present in the original input video, and if this noise is amplified, the output result flickers. But still there's some more flickering, and this more flickering is caused by ambiguity. So for example, let's assume that we have these two styles, so we are transferring from the left image to the right image, and I marked these two patches here, so the other one is not that visible, maybe here, but it's here. And if we take these two, the black patch and green patch of the input image, they look very same. They both have black color, but in the output image, one patch is more whitish, and the other is more bluish. So this means that we are training network to stylize like there's ambiguity during the training. Network is learned to stylize one patch to many different outputs, which is not good. So to solve this, we propose to use this auxiliary Gaussian mixture. So it's also described in our paper. So I will just quickly go through it. So the network is fully convolutional. There is we can add more channels to the network. So we propose to add 3 more RGB channels. So not only the input RGB image, but also like these 3 channels for the Gaussian mixtures. And the network works just fine if the input channels are aligned. And how to create these Gaussian mixtures? So these Gaussian mixtures are randomly created, but they are propagated through time. So for the input sequence that we know, and this can be computed also in real time, but let's say for the input sequence we know ahead of time, we select one frame, we randomly compute or randomly create these Gaussians, and then we use as rigid as possible image registration to propagate these Gaussians with the changing content of an image. So it looks like this, and if there is so there will be some holes after time if the content is changing. So we just fill these holes basically with more random Gaussians, and we again propagate these Gaussians in time, so that Gaussians are in line with the sequence the whole time. And here we take the final stacked Gaussian mixture layer, and we train the network on it. And finally, using this other trick to make it more temporally coherent, we were able to obtain good stylization results that don't flicker. All right. So what happens if there is need for more keyframes? How do we handle more keyframes? So it's quite straightforward. So let's say there is object that is moving or rotating ahead in this case, for example, and the side of a head is not well stylized, as you can see, because there is in training frame there is something missing, right? So there is the side of a head is not present in there. So we can easily we ask artists to paint side of a head, and because we are using training patch-based training strategy, during the training we can restrict for the second keyframe, we can restrict to sample patches only from this particular area, so the network can quickly learn just the important parts, how they should be stylized. That's it basically for the entire method. So I will just now quickly present some more results. And we already saw a lot of results. So this is our approach now in this video refers to the approach I just talked about. Output of Jamriška is the last approach Daniel talked about. Okay, so quickly moving to the results where there are multiple stylized keyframes. So in this case, there are 4 keyframes I think used. And again, these keyframes, if there is if we are not able to capture all the content in one keyframe, we need to provide more keyframes if you want really good stylization results. Yeah, and thanks to our patch-based training strategy, and thanks to the optimization that we really focused on interactivity, on short training times, we were able to come up with interactive scenarios like these. So we have a camera is capturing what the artist is painting, and we train the model on the fly. So actually we start with a model that is initialized randomly. All the weights in the model are initialized randomly, and within just a few minutes we train on the keyframe that artist is painting, we train the model from scratch. Okay, and I will move to my last result. So we presented this technique last year at SIGGRAPH as a technical paper, and we also presented this technique at SIGGRAPH real-time live session. So at real-time live session, we presented this this interactive use case. So here my colleague is painting image of me. There is a camera that is capturing what she paints. The camera is connected to one computer, but this computer doesn't do anything. This computer just takes the images and sends the images somewhere to cloud GPU where the training is running. So there's cloud GPU running the training. And here I am sitting in front of my laptop, and on this laptop there's quite a good GPU in this laptop, and inference is running on this GPU. So this laptop takes the models from the server where the training runs. Every few seconds it loads new model weights, and it stylizes my face. And again, we were able to, or this model is trained on the fly while she's painting. The model is being trained, and within just like after just like few minutes, maybe 2-3 minutes or 4 minutes, we were able to get results like this. So in this case, the quality is not perfect. We really optimized in this case. We really optimized for speed and interactivity. But yeah, that's it. So thank you for your attention, and I hope there are some questions.
Well, thanks a lot, Andre and Daniel. This was I knew the result, but it's always impressive to see them again. Like it's really like a gorgeous result that you have shown us, and the technique is impressive. So I invite people to ask questions in the Q&A pod of Zoom. That's at the bottom. We have a few. And just while people put questions, a quick plug. So this was last year's result at SIGGRAPH, and there's more coming this summer. So don't forget to register and attend. And there. So let's go to some of the questions that we received. So the first one is, do you think that audience can choose their desired style to watch movie or games in the future in real time?
Mm-hmm.
I think what the person has in mind is that I have on TV, I'm streaming a movie, and I can choose. No, I want a Van Gogh stylization of that movie on the fly. Okay. Do you see that coming?
Yeah. So that will be definitely possible in the future. Maybe not in like near future, or depending what you want. Like if it doesn't have to be perfect, there are some methods that can do this even now to do some kind of stylization. But yeah, I think this is nice use case, and it might be like ultimate goal for us to try to really push state of the art in style transfer forward, make this possible. Daniel, do you have some comments regarding this?
Yeah, I think that's a great idea, actually, and it would, let's say, require the artist to prepare more styles for the particular movie, which would be like, I can imagine like at least the production will have money for one style, and then maybe if it will be, like, say, even, let's say, cost effective, they can create also more of them. So essentially, sure, so we can have the same movie and stylized using different artists, for example. So that's definitely feasible.
Yeah, thanks. So another question is that how did artists react when they use the system for the first time? And I think it's based on your introduction where Daniel, you said that the motivation came from artists who wanted this more like real material feel compared to CG. And I think you also mentioned later that some of the results the person working is using production. So can you tell us how they reacted, but more also in general, your experience with the real world of production and artists using your system?
Absolutely. So there are actually two types of artists, and one type is excited. So they see there is a great potential in that method, and they actually already think of some, let's say, workflows, how to actually use the technique in the real pipeline. And there are some other, let's say, part of or artists or a group of artists who are scared, actually. So they are like, oh, no. So they are just, let's say, kind of, let's say, taking my talent, actually. So they are copying my skills that are developed over years, and they now can create the entire movie using myself. This is super scary. I would like to, let's say, just get rid of it as soon as possible. So that's the actual two types of reaction we typically get. But I think it's kind of similar to what, for example, happened when there was like hand-drawn animation and then the actual CG started. So at the end, I think there is no like kind of like these who are just doing the hand-drawn probably has, let's say, a smaller amount of work that they have to do. But if they learn how to do the new thing, how to actually use the new techniques, they can still work on new amazing movies, and it just requires to learn new things. So I think this will be the same scenario. And of course, it takes time to kind of accommodate to this new type of animation or creating an animated movie. But I believe the more we will be pushing and providing tools for artists, the more they will also get used to that and be able to produce some content using this new approach.
Thanks, Daniel. So I have another question. So let me try actually this. So what type of styles work best with this technique?
Yeah,
Andre, if you want to.
Okay, yeah. So like again, it depends on the technique. So in our today's talk, we presented like that. Daniel presented a lot of our techniques or techniques he and our lab, his lab at CTU published. But if this question is for the technique I presented, it's it kind of works with any styles. Of course, in some styles, it's much easier to hide some artifacts. So and of course, if the style, if there are some, like for example, regular patterns in the style, I don't know, like shirt with like checkerboard pattern or something like that, this might not be preserved well. So if there is some like some usually if there is some regular structure, this structure gets distorted and it's like a giveaway. It's like, oh yeah, so this was stylized, or this was not, like this was stylized by computer, because artists would not paint it like that. So I would say regular structures might be a problem, but apart from that, everything works as it works.
Okay. So I have another question. Is it possible to get even better result if one has time to wait longer than a minute? Because you presented in your thing, say, oh, we want it to be fast in a minute, but if I'm doing a movie, I can wait overnight, right? If that's going to give me even more impressive results. So can you comment on that?
Yeah, so it's a question for me, I guess. Yeah, so definitely, like stressing the training for 1 minute is it was really just for the purposes of interactivity. And of course, if you wait more, for example, 5 or 10 minutes, I think we did a lot of experiments with 10 minutes, and after 10 minutes, the network is quite well converged. So waiting 10 minutes, you probably get the much better results, and you get optimal results. After 1 minute, the results are not that optimal. They can be better.
And usually, if you, let's say, run the computation for a longer time, the improvement is almost negligible. So typically, like 20 minutes for, let's say, 1 megapixel, let's say, image is reasonable for getting like decent quality. And then it's, of course, wasting some power, but there is not much improvement. Yeah.
Thank you. So as an artist, is there anywhere to experiment with this system without implementing the software myself based on the paper? Presuming that I've got the appropriate hardware. So I think it's your fan club start to speak.
Yeah. So this current system is we have a GitHub repository that is publicly available. So anyone can go and download this GitHub repository. It's in Python. It should be doable. Should be quite easily doable. But maybe it's not like a tool artist would would want. It's Yeah, but we open source it. It's available for everyone who is not shy or who can deal with the Python.
And also the previous technique, which was the patch-based one that we discussed, is available. So actually, our colleagues Andrei Amrishka and Sharka Sokolova are actually starting a company, and they are developing this particular tool for, currently it's available for free, but it will be like a commercial version tailored for real production. So definitely this is another possibility how to play with it. It's called ebsynth. So you can find it, ebsynth.com. Yeah, you can download it as well.
Okay, thank you. So I have one more. You made a bunch of somewhat counterintuitive advances to achieve these impressive results. Did it surprise you that this worked, and what other improvements are you investigating?
Yeah, so who wants to answer that?
You are the first author.
Yeah. So well, yeah, like of course, like it kind of surprised us that it worked. Like we had some intuition why. So I think it's usually like doing research. It's usually you have intuition. Okay, so this should work or because of something, or this should not work because of something. There are some like mathematical or other leads kind of telling you if this makes sense, at least to try. And then if you try it and if it works really well, you are kind of half surprised, half happy. So yeah, so definitely we had a reason why to try this. So it was not like pure surprise, but we were really glad that it worked out as it did, that it worked really well. And yeah, we are working on some other improvements, of course. There's one more paper we didn't describe in our talk. Maybe we should have Daniel and some other colleagues at CTU. They just recently published paper, Stalp. If you want to just quickly, Daniel, tell something about it.
Yeah, so this was presented at Eurographics this year, and it's an extension of this neural-based technique, which is also training, but in this case, it's full frame, so there is no patch-based strategy, and there is using a different technique to avoid overfitting, which is, let's say, using some BGG loss on the other frames. And it actually has the advantage that you don't need to create, let's say, a larger amount of keyframes, because the previous approaches that we discussed today, for let's say if there is like change in the scene, so after a while they will break, so you will easily see some artifacts. But this new technique, which is kind of regularizing and using other frames from the sequence to do this regularization, gives you the possibility to decrease the number of keyframes that you are actually need to produce. But the downside of this new technique is slow. So it really requires hours to do the actual training. So it's not ready for interactive. So maybe it's not practical for real production. So that's a kind of like an alternative. So now we will probably would like to merge somehow these two in a way that we will get something which is practical on one side, and on the other side, it should also not require too many keyframes. Yeah, so that's the holy grail actually that we like to achieve.
Thank you. So I have one more question, which I think is your user base continue to grow. What is the best way to shoot the video for this technique? What to avoid?
Yeah. Okay. So as I already talked about, the noise, like if there is some noise in the video, even if the noise is not visible, it hurts the performance. So we present it a way how to get rid of this noise. But of course, if the noise is not here in the video in the first place, it's better. And yeah, like apart from that, it works with arbitrary videos. So it doesn't have to be on a green screen. It doesn't have to be with like any markers, anything like that. But of course, it might help if the because the system works on in RGB space. So it's probably a good idea if you can do these modifications. If you cannot, that's okay. But if you can, green screen and some clothes that are maybe far from each other in terms of RGB distance would be good. So like a person wearing a green shirt in front of a green screen is not a good idea. Yeah, so I think this is.
So the other important aspect is lighting. So typically what is best is to have some diffuse lighting in the scene. So some strong shadows typically cause problems because like it really changes the appearance of the original scene, and you would like to stay kind of close to the appearance of the keyframe. So if you change the light source position so it will create hard shadows, then typically it will not work. So something which is more close to the actual let's say ambient illumination. And of course, you can create shadows in the style. So that's kind of like you can stylize the scene in an arbitrary way because the original content is kind of, let's say, discarded from that point of view. So you can stylize it different as you want. Yeah.
I see one more question. So, thanks for the talk. Notice most of the examples were live action. How about using this technique on CG animation as opposed to live action content? For example, can this software be utilized on an animation to stylize the 3D models? I would assume the same methods would apply. To add, in terms of future application, since PBR was brought up, could you see this as being a viable method for stylizing real-time graphics such as video games?
Okay, so should I go ahead?
Yeah, Andre, that's good.
Yeah. Okay, so I think the answer why this was why most of the results are live fiction is that we have a couple of other papers that are doing 3D, and we have in these other papers it has to be 3D because there is some there are some assumptions. There are some we use the 3D rendering in a way that we have to use 3D. And this paper, I think we were like super excited that this paper is not tied to 3D in any way. So this paper, this technique can work on arbitrary 2D scenes. It can work on live action content, which is like much harder than for us it was it's much harder task than doing something in 3D. In 3D, you can do some modifications. You can do some lighting things. You can export different lighting channels, light path expressions from the 3D and stuff like that. But you cannot do it in this case. So yeah, so we were excited about this. We created a lot of live actions, and yeah, but of course, like this technique can be applied on 3D in exactly the same way. So you have a 3D model, you stylize this 3D model from one angle, and then you rotate the 3D model, or you rotate the camera around the 3D model. And as long as there is no new content or no like significantly new content not seen during the training, it should work quite well. So in stylized games and stylized games, it would be super cool to have this in games. And maybe Daniel wants to comment also something on this. We have other approaches that are more suitable for games, more tailored for 3D games.
Of course, yeah. So we have versions of the algorithm which is kind of approximative and can run in real time. And we have also, let's say, Unity plugin that's able to kind of achieve similar stylized look. So you can already try it. So it's called Stylized, and it's also available on my homepage, so you can retrieve it. So this is an instance of possibility to, let's say, do stylized games in the future. But of course, there are some limitations. So you will see that maybe it will not work as you would expect. But we actually envision to get into state that we will be faster, will require less keyframes, and will get the highest quality as possible. This is our ultimate goal. So maybe in future we will deliver something which will merge all these efforts together to create something like a new way of creating game content in future. Yeah.
Thanks, Andre and Daniel. I think we could go on for quite longer, but we also at time, and I want to be respectful of your time and the time of everyone. On the chat, there was a lot of excitement and people saying thank you, and I really appreciate your talk. So that was a really good presentation, very impressive work. I want to thank you again for joining us today. And I want to remind everyone, like, attend SIGGRAPH this summer and continue the experience, like more to come. And again, fantastic to have the two of you with us today.
Yeah, thank you. Thank you very much.
Thank you very much for joining us.